Welcome to Brain Vision.
Derivatives, using those to find approximations. And with this question, we're going to be using a linear approximation from a table that we're given, the table in example 3. So note that when we do a linear approximation, the formula for that will be taking our original function, add that to the partial derivative with respect to x at a particular point, and add that to the partial derivative with respect to y, again at that particular point, and then multiply it by the difference between y, our approximate y, and the point we used. Okay, so in this case, our x and y is really going to be temperature and humidity. And we'll use, so we have a 94 degree Fahrenheit temperature and an 80% humidity. So this means our linear approximation at temperature and humidity is going to be equal to this function at 94 and 80 plus partial derivative with respect to the temperature at 94 and 80 times t minus 94 plus the partial derivative with respect to humidity, again at this same point, 94 and 80 times h minus 80. And of course, if this is our linear approximation, then this would also be roughly equal to our function at that same point. So from the table, finally getting into what we need the table for, we have f of 94 and 80 is equal to 127. So we're going to find the partial derivative with respect to the temperature by fixing h equals 80 and observing the variation of f with respect to t along that fixed value. Okay, so we can consider a new function. G of t is equal to this function of t where the humidity is always 80. Okay, but we want to do that specifically where t is equal to 94. And the derivative of g of t would be the derivative of f at that point, right? So if we take g prime t, is going to be the limit as h approaches 0. Maybe we shouldn't use h because of the humidity. Let's say j of g t plus j minus g of t. This is just our standard definition, but this is also equal to the limit as j approaches 0 of f at t plus j 80 minus f of t and 80 over j. Okay, so if you want to plug 94 in there. We can find the value as t changes from 92 to 94, and then from 94 to 96, and get the approximate value. Right, so let me say g prime of 94 would be approximately equal to f of 94 plus 2, 80 minus f of 94, 80 over 2. Okay, and then this is going to be equal to 135 minus 127 over 2, which is equal to 4. Then we do the same thing, but for minus 2. So it's also going to be equal to f of 94 minus 2, 80 minus f of 94, 80 over 2. This gives us 119 minus, that'll be over a negative 2, apologies. So 119 minus 127 over negative 2 is equal to 4. Okay, so then we want the average, so the partial derivative with respect to t at 94 and 80 is going to be equal to 4 plus 4 over 2 is equal to 4 again. It's a popular number. Okay, so we're going to do the same methodology. I'm going to leave out the sort of background motivation for it this time. So the partial derivative of h then is going to be roughly f at 94, and then we'll do 80 plus 5 minus f at 94, 80 over 5. Okay, which is equal to 132 minus 127 over 5, which is equal to 1. It's also going to be approximately equal to the same thing, but where we subtract 5 instead. So 80 minus 5 minus the function f at 94 and 80 over a negative 5. This gives us 122 minus 127 over 5. Negative 5 is equal to 1 again. Okay, so now we want to take the average, right? So we get partial derivative of f with respect to h at 94 and 80 is equal to 1 plus 1 over 2. It's equal to 1. Okay, so that means our linear approximation at t and h is equal to 127 plus 4 times t minus 94 plus 1 times h minus 80. Okay, well this ends up being equal to 4 times t plus h minus 329. So the estimated heat index is going to be this. So now we want to plug some new values in to get our estimation. So you could then estimate that f of temperature is equal to 95, humidity equal to 78, will be approximately equal to L, our linear approximation at those values. And that will then be equal to 4 times 95 plus 78 minus 329. And the handy dandy calculator says that is equal to 129.